All right, hello there. So I actually didn't get too far into the last video, and I realized I accidentally spoke. I got excited talking about vectors, and I raised my voice probably more than I should have with the microphone. And so if I've done that in the past since I've gotten the microphone, I apologize. Thankfully, I was early enough in the recording that I could just stop it and start over. But anyways, this is video number 3 of section 4.1. So we're going to start this video much like we did the previous by looking at a set and showing that it is a subspace of Rn. Then we're going to generalize some of these ideas to all vector spaces and not just Rn, and generalize some past definitions which we had looked at, and generalize those. And then we're going to end by doing what I think is one of the most fun problems in math and what had gotten me excited last video, which is just being given this set and having to determine if it is a vector space or not. So having no idea, just saying, is this set a vector space, and having to figure out, okay, is it a vector space? And I think it's a lot of fun to do, because you get to work through these examples and you get to think, okay, is this proof work? So we'll do that at the end. Anyways, so if I've got n greater than or equal to 2, we're just going to let v1 and v2 be vectors in Rn. And what we want to do here is show that the span of v1 and v2 is a subspace of Rn. So if you'll remember, the span of v1 and v2 contains all vectors of the form and we'll say all vectors u of the form u is equal to c1 times v plus c2 times v2, where here c1 and c2 are just real numbers. So remember, this is a linear combination of v1 and v2. And so, you could alternatively define the span to just contain all linear combinations of v1 and v2. And so we want to show that all vectors of this form a vector space, specifically a subspace of Rn, right? And we know that this is a subspace of Rn because ultimately all of the vectors that are in this set, right? So we're talking about this set, which is span v1, v2. They're all going to be vectors of length n, right? So certainly this is a subset of Rn. So because of that, and because that we know Rn is a vector space, we only need to verify the 3 properties of being a subspace. Of course, to show that this is a vector space itself, but we'll also show that this is a subspace of Rn by doing that. So 3 things we need to check. And to do so, again, we're just going to define 2 arbitrary vectors in this set. So I'll sort of restate this for the purpose of the proof. We're going to let u1 equal c1 v1, or u be that. And we'll say w equal d1 v1 plus d2 v2. I missed a great opportunity. If I'd called these, instead of vectors, if I'd used, or instead of v, if I'd used r. No. Anyways, I was trying to make a Star Wars joke. This almost sounds like R2-D2. But so we're going to consider these 2 arbitrary vectors for the purposes of our proof. So first things first, we need to check, is u plus w also a vector in the span of v1, v2? Well, notice this is equal to the vector c1, v1 plus c2, v2 plus d1, v1 plus d2, v2. And this might look like a long jumbled mess of a sum, but rearranging everything around, we can rewrite this like so. So what does this do? Well, notice that we've now written u plus w as the sum of a scalar times v1 plus a scalar times v2. And so this means that the vector u plus v is also in the span of v1, v2. And so this is closed under addition. For number 2, well, we need to show that the 0 vector is contained in this space. But remember, I can let C2 and C1 be any constants I want, so I'll just let them both be 0. Then notice 0 times v1 plus 0 times v2, which is a linear combination of v1 and v2, is equal to the 0 vector. And so the 0 vector is also contained in the span of v1, v2. Finally, we need to show that this is closed under scalar multiplication. So I'm going to let, let's see, we've used C and D. We'll say A be a scalar. Now let's look at A times W. And so this is A times D1, V1 plus D2, V2. And this is equal to A times D1 times V1 plus A times D2, V2. So notice I can distribute the A through each of these terms. And then because I have the nice properties that I can sort of shift the scalars around, or the order I multiply, notice I've written A times W as scalar times V1 plus scalar times V2. And so this is also closed under scalar multiplication. And the span of V1, V2 is, in fact, a subspace of Rn. All right, we can generalize this idea quite a bit. And so I wanted to give this example because we talked about this idea of span and linear combinations with vectors in Rn. But we can talk about the idea of a linear combination with any set of vectors in any vector space. And we can generalize this idea of the span of a set of vectors being a subspace to any number of vectors. And so you can actually then sort of go through the same proof steps that I just went through for 2 vectors for any number of vectors in a vector space V. So we'll go ahead and state these sort of more general definitions now. Note they're going to look quite similar to the previous definitions, except now we are stating them for any set of vectors v1 through vp in any vector space V. In a vector space so notice here I'm not assuming V is necessarily Rn. So these could be any sorts of vectors. We say that a linear combination of these vectors is any vector of the form And so we're, again, defining this identically to how we defined linear combination before. all we're doing is expanding this idea to allow for any types of vectors, or any type of vectors. And so notice in particular here, this makes sense, right? Because I still have vector addition. And if I've assumed that, right, this is a vector space, then of course scalar multiplication is closed under scalar multiplication. So this expression makes sense with any set of vectors and in any vector space. And so this is just a linear combination, again, defined in the same way, but now for any set of vectors in any vector space. And so, much like we did before, for a set of vectors, v1 through vp, the set span of v1 through vp is the set of all linear combinations of these vectors. So again, we're defining span now in the same way. It's just all vectors of the form c1v1 plus c2v2 and so on. And so what we had previously shown was that if I had two vectors, that the span of those two vectors was in fact a subspace, right? And we were doing that in Rn, but you could actually go through at no point in that proof, in that first example I showed this video, did I actually ever really need to use the fact that those vectors were in Rn. So that proof could immediately generalize to any two vectors in any vector space V. But you could also, and I might have this as an exercise, you could actually also generalize that proof to any number of vectors, and that is the big theorem we will state today, that if I have any set of vectors in any vector space, is a set of vectors in a vector space V then the span of that set of vectors is a subspace of V. And you can actually just walk through that proof, and everywhere where I have an expression with two vectors, you just sort of generalize it to have more. Right, so for example, if you wanted to show the zero vector was in this span, you just let each of these constants be zero, right? And when you want to show closure under addition, you just group all of the like terms together. And so you can very quickly generalize the first example to prove this theorem, that if I have a set of vectors in a vector space V, then their span is always a subspace of V. And so keep this theorem in mind, because this will be very foundational to what we're going to talk about in future sections. So this is the first big reveal, or I guess the only real big reveal of this video. I just want to wrap up with one fun example. So what we're going to do is we're going to be given a set that we've potentially never seen before, and we have to determine if that set is a vector space. So we're going to let H be the set. This will look a little bit like the example we did last video, but with a slight difference. Of all vectors xy such that xy is greater than or equal to 0, and we want to know, is H a subspace of R2. So just looking at this question right off the bat, this reads H is the set of all vectors x, y such that the product x times y is non-negative. Certainly, looking at these vectors, they're all vectors of length 2, so we know that H is at least a subset of R2. But we want to determine, is H a subspace? So I sort of have an order I like to go through when looking at this. Generally, the easiest one to break, if it's going to break, is H containing the 0 vector. So first I'll ask, does H contain? Well, here the 0 vector is going to be 0, 0. Well, certainly 0 times 0 is greater than or equal to 0. So the answer here is yes. Right, and so this rule, the 0 vector rule, easiest to break. Here it's not going to break. So if we're going to show that H is not a vector space, we have to show that either it's not closed under addition or not closed under scalar multiplication. Generally, next, I like to go for addition. And so what you want to do here is you want to initially try to break this, right? So I want to try to find potentially 2 vectors themselves that are in H, but whose sum is not in H. And what you want to start doing is thinking like, okay, if this is going to break, how is it going to break? Well, so certainly, right, I want some vector where the x term is negative and the y term is positive, right? Because that will break this requirement. I'm allowed to have both negative and both positive. So what if I had something like this? Negative 2, negative 5. And we'll let this be u. And we'll let v equal, we'll say 3, 4. So looking at this, you might agree that each of these vectors is contained in H, right? Well, okay, so if each of these vectors is contained in H, then their sum should be contained in H. But notice their sum is 1, negative 1, and so this is not in H. And so this is not a vector space. So generally when presented with this question, I'll go through this. You could actually show here, I did it in the order I always do it because this one, I find that addition tends to be the one that's going to break the most frequently if some rule is going to break and this isn't a vector space. You could actually verify, if you want, on your own, that in fact H is closed under scalar multiplication. But here we can see that H is not closed under vector addition, and therefore H is not a subspace of R2. Usually, so after checking a few of these, if I sort of check a few basic examples that I can think of, after that, if I haven't broken it yet, right? So if I hadn't found a counterexample like this, what I might have done is then looked at 2 general vectors, right? So replaced these with sort of just general, like u1, u2, v1, v2, or variables, and tried to sort of work the other way. So generally what I'll first do, given this question, is try to disprove it. And if I try and just can't seem to disprove it, usually that will kind of lead me to how I should prove it. So there'll be a few more examples like this, certainly on your homework and at the end of these notes. But yeah, so this is section 4.1, and so tomorrow we'll move on to 4.2.